Welcome to the fourth video in the series of lectures on SQL. In this video, we're going to get to some of the more serious data analysis by looking at aggregations and joining tables together. Now, these concepts aren't new since we already reviewed them or already learned about them in the context of pandas. And they're going to look very similar in SQL. In fact, it's going to use a lot of the same verbiage that we learned when we learned about these topics in pandas. Remember, data aggregation refers to when we calculate some summary statistic like a count, a sum, a max, or an average across a group or collection of data. So for instance, we can select the average price or the max price from some table. And that's pretty simple. This is equivalent to, in pandas, if we had our products table, simply aggregating it using a mean and a max. Only, of course, we selected the price column. There we go. So in SQL, we don't have, this method notation or this object-oriented approach. SQL is, I believe, what's called a declarative language. Yes, declarative query language. So we simply kind of say, more or less in like plain English instructions, we state our expression and evaluate it. And I'm going to take a brief aside just for a second to comment that something I haven't highlighted throughout this notebook is that SQL reads a lot like plain English. And while I think Python is extremely readable and does a very good job of selecting commands and keywords and even shaping its syntax around being readable almost like plain English, SQL is even closer to plain English due to its highly structured nature and its restrictive scope in what it is trying to accomplish. And just like in pandas, kind of coming back to the main thrust of these lectures, when we perform aggregations, we often want to aggregate not over the entire table, but on slices of the table, where we group the data based on the values in the table in some column. So for instance, if we wanted to get a count of the number of orders that are being delivered to each country, we could select the delivery country and the count of distinct order IDs from orders grouped by country. So here we have the first 10 countries, and by default it's just ordered in ascending order by delivery country. And we see the counts of the orders being shipped to each country. We could, if we were interested in which countries are receiving the most shipments, order by, well, we would want to order by this count. How can we do it? Unfortunately, there's no convenient name for this count. So we'll actually add an alias for the count, where we'll alias it as count. We'll give it a name. We'll order by count in descending order, so we see the countries receiving the most orders first. And here we have China and India receiving the most, followed by Germany, Russia, Japan, South Korea, etc. Aliasing is very useful in SQL for these kinds of operations where we maybe perform an aggregation and then want to use that aggregation for filtering or sorting or making subsequent selections for further processing. So we assigned an alias using the as keyword, and then we used that alias to perform sorting. And notice it also renamed the column in the output. Now that we understand how to perform... Oh, right. By the way, the aggregation functions that are available also depends on what flavor of SQL you are looking at. For instance, whoops. Let's see here. Mean. So there is no average or mean in SQLite. However, AVG. Maybe that's why I'm not getting anything. Oh, right. I used average earlier. I forgot. Is there standard deviation? So, there is no standard deviation in SQLite. However, I believe there is in other flavors of SQL. So for example, in Microsoft SQL Server, there is a standard dev aggregation command. So as I was saying, unfortunately, which aggregating commands are available is somewhat SQL flavor dependent. Not strongly. Most of them will be available in all flavors of SQL, but it does vary a little bit from each to each. Something that does not vary much from SQL flavor to flavor is joins, which are one of the more commonplace operations in SQL and which can be performed in many different ways. Similar to pandas, in which we can perform joins in many different ways, using merge, or join, or concat. In pandas, the main ways to perform joins are using the join keyword, or by selecting from multiple tables and using the where keyword. So if we want to, for instance, calculate the total revenue that we have received for our orders that we've sold from our shop, we'll want to sum up all the prices for all the items purchased in those orders. So we'll need to join the price information from the products table to the orders table. The orders table and the products table share an attribute, product ID. So we're going to select the sum of the price from orders, which we're aliasing as O. So we're going to call orders table O for short. And we're going to select from table P the price column, where we're performing a sum. And we're joining that products table, which we're aliasing as P, where O product ID equals P.ID. So we have our products ID column being equal to our orders product ID column. Now, this is one place, unfortunately, where reading SQL code is a little bit not so straightforward, because we're selecting something from table P, but we don't know yet what table P is until we read further in the query. But still, this is pretty easy to understand. We're dealing with orders, which is aliased as O, and products, which is aliased as P. We're joining them together where these columns have a match, and we're going to sum up all the prices from table P once we perform the join. We could perform the same join by selecting, again, P price from these two tables where the product ID from P is equal to the product ID from O. And we get the exact same answer. Notice this is a different answer than if we just selected the sum of price from products. So this is the total price if you wanted to purchase every product in the store one time. But of course, our orders consist of many repeated products, so this is the total revenue from all of our orders. Every time we find a match between product IDs in the orders table and product IDs in the products table, we join in the product price from the products table. We can perform all the same kinds of joins, inner, outer, left, and right, that we learned about when working with pandas tables. We specify those by simply saying inner join, outer join, left join, or right join. Since we specified these tables with foreign keys, there's not going to be a difference between those various joins in this example, because for every order with some product ID, that product exists in the product table. We can combine joins with aggregations to answer more interesting questions. For instance, if we wanted to see the amount of money that particular customers had spent in our store to get an idea of who our most valuable customers were, we might sum up the prices of what they had spent on their orders and print out their names along with the total amount of money they had spent. So we'll select the name from the customers table, aliased C, and the sum of the prices from the products table, which we're aliasing as P. And we're joining all three tables together, where product ID in the product table is matching product ID in the orders table, and customer ID in the customers table is equaling customer ID in the orders table. Here, I've omitted the as keyword for brevity. It's not required, although it does add clarity. We're computing these total amounts of money spent for each customer. So we're grouping by customer ID. And then we're going to order by total, since we want to see who has spent the most money. So we'll order in descending order. So here are our highest spending customers in descending order. Now we're going to try something even more complex. Let's find the total amount of money spent on orders that are shipped internationally for each billing country. So where the billing country does not match the delivery country. Remember, we have billing countries as well as delivery countries. We're interested in the amount of money spent on orders where billing country does not match delivery country. So we'll need to join the customer's data to the orders data to compare the billing countries. Then we'll need to filter out the rows where the billing country doesn't match the delivery country. Finally, we'll need to join the price data from the products table to that filtered result so we can calculate the total amount of money spent on orders shipped internationally. We begin with what's called a subquery. This sets up a table that we're going to make a selection from for our final aggregation. So we're going to select billing country, which will alias as bill, delivery country, which we're aliasing as deliver, and the total price, which we're aliasing as revenue, REV. From all three of our tables, where we've joined them together based on customer ID for the customer data and product ID for the product data. This is similar to what we've seen before. And we're grouping these results by bill for the billing country and deliver for the delivery country. And we're summing up the price for each combination of billing country and delivery country. So the total revenue for every billing country, delivery country pair. But we're going to additionally filter out where all the rows where billing country and delivering country are the same. So we're specifying we only want groups where bill is not equal to deliver. When we're doing a group by, we can filter the results using the having command. So we're interested in groups having bill not equal to deliver, the groups that are shipped internationally. This result we're aliasing as SHP for ship. But this is not the final result. We want the total money spent in each billing country from the orders that are shipped internationally to different delivery countries. Right now, we have something like this. Whoops. Not quite. Here, SHP. Oh. There we go. So we have groups where we have total revenue from each combination of billing country and delivery country. But we only want revenue for each billing country. And we want to essentially sum over all these totals for the different delivery countries. So from this result, which we've aliased as SHP, we're selecting the billing countries and the sum of all the revenue for that billing country. So all of these numbers for Algeria. And we want to group our result by billing country. We want a total revenue for each billing country. And finally, we'll order by descending amount spent. So it looks like in our data, Germany spent the most money, or German customers spent the most money sending products internationally, followed by China, India, the US, etc. As I mentioned, this is called a subquery, and I mentioned briefly earlier, we often use subqueries to build an intermediate result that we will use in the calculation of our final aggregation. This can be pretty difficult to get a hold of and practice. I highly recommend that you try for yourself let's see here, some SQL exercises on HackerRank. So HackerRank, which I mentioned in a previous lecture, hackerrank.com, has a variety of coding challenges covering different topics. And one of the domains in which they have challenges is SQL. And it can be really useful just for practicing basic SQL syntax, as well as practicing your aggregations and joins. So this is a very useful resource for seeing more examples and working through examples yourself. There's a little bit more information down here about connecting to databases from Python, as we did originally to load those CSVs into our database via pandas. Remember, we constructed a database connection using this SQLite Python module. As the name suggests, that module is useful for creating connections to SQLite databases. I mentioned also some other flavors of SQL, like MySQL and PostgreSQL, which have their own Python modules for making connections. Next week, we'll be talking about another package called SQL Alchemy, which can not only provide a database connection, but also can perform a task known as object relation mapping, which is useful for seamlessly integrating relations from a database where we might store data for our application into objects that we can work with easily within the object-oriented world of a Python application. So that'll be next week's lecture topic. I'll have one more video that will be very brief, in which I discuss some of the differences between these different flavors of SQL, and when you might want to choose one rather than another for an application.